Hello everyone, this is Professor Kuehn. In my last lecture, you might recall we had been discussing Galileo's Dialogues Concerning Two New Sciences, Chapter 2. In this chapter, Segredo, Salviati, and Simplicio were trying to wrestle with the question, what is it that holds substances together, or what provides for the coherence of substances? And one of the ideas they were exploring was the idea that nature abhors a vacuum. That is, nature seems to act in such a way as to prevent a vacuum from happening. And the idea that Salviati was presenting is that nature's abhorrence of a vacuum is what accounts for the coherence of substances. So if you try to break apart a stone, at least momentarily, one will need to create a small gap inside of the stone, a vacuum. And because nature abhors a vacuum, she prevents that from happening, and that's what holds the stone together. Then what happened is Segredo and Simplicio and Salviati began to question what kind of the mechanics of how this would work. And there were some problems that Segredo was raising regarding how one should think about nature's hatred of a vacuum creating this kind of cohesive force. And this got into kind of a philosophical topic. And you might remember at the end of that discussion, Salviati basically brought them back and said, okay, for whatever the cause of this, we should be able to, if nature in fact abhors a vacuum, we should be able to measure how much nature hates a vacuum. And so in this lecture, we're going to be talking about how Salviati presents an experimental apparatus for determining how much nature abhors a vacuum, to see if this can numerically account for the kind of cohesion that is apparent in many substances. So this is right around page 16 of chapter 2 of A Student's Guide. And I'm going to cut away from this view that you're looking at right now and open up sketchbooks and draw some pictures. Okay, so this here is the chapter we're looking at, the coherence of substances. I'm going to jump ahead a couple of pages. And on page 17, there's figure 2.1. This is Galileo's apparatus that he presents to measure the force required to break a column of water. So how he explains this is the region ABCD, you might think about that as a cup, an inverted cup. And fitted in the bottom of this cup, maybe I think he calls it a glass or a metal cylinder. And inside of this, there's a wood plug, EFGH. And this plug fits nice and tightly, but it's able to slide in and out of this cup. Drilled through the center of this plug is a hole, and through this hole there's this shaft I that's fed, and there's a hook on the end at position K, and hanging from this hook you can place a bucket or you can put weights in it. And the idea is that you can kind of push this plug I up through to allow a gap, and then you introduce water into that region, I guess a region above the plug, and then once you pull that shaft down I, it seals that region and you have water filling that region. Then what you do is so water is completely filling the region where that letter I is located, and it's plugged off. And then what you do is you begin hanging weight. You maybe pour lead shot into the bucket K, and you'll find that the water completely fills that region inside of the cylinder until you put a critical amount of weight on it. And once you put this critical amount of weight on it, then that plug EFGH begins to slide downward, and the water goes down with it, and you get a region above the water where a vacuum is formed. And so this presumably what Galileo is saying is we can measure the force that it takes in order to create a vacuum. This is precisely what he does, and we're going to be doing something like that in lab, but instead of using a bucket and a bucket like this full of lead shot, what we're going to do is use an inverted syringe. So I'm going to make a drawing here. You might imagine a syringe like this, and you put a plunger into the syringe like this. So this is the plunger, and the plunger like this fits nice and tight in there. And then what you do is you take the syringe, you dip it into water, and you suck water into it. So I'm going to go like this to indicate that there's water sucked into it. And then what we can do is to make sure that there's no air in here, you can push the plunger up a little bit until water squirts out the top. And then what you do is you put a cap, we're using a lure lock cap, screwed on the top, that seals it. Okay. And then what we're going to do is we are going to tie a string of some sort to this and hang weights. So we're going to apply a force or a weight downward, force or a weight down. And what we can do is we can measure the amount of force it takes in order to create a gap above here. And that force is essentially the force with which, or the strength with which nature abhors a vacuum. This is the strategy that Galileo is presenting. And it just so happens we'll find that if the area of the plunger, and by the area I mean the area of contact with the water above, so the area right there, if that area is equal, if the area is 1 square inch, of course most plungers aren't squares, but it's going to be some circular area. But if you convert that into square inches, if the area of the plunger is 1 square inch, we're going to find that the force it takes is about 14 pounds. So that's the force that we will find that it takes in order to create a vacuum at the top. If the area is larger, we're going to find the force is larger. If the area of this is smaller, we're going to find the force is smaller. In fact, we're going to find the force that it's required in order to create a vacuum is going to be proportional to the area itself. So what we mean by that is we double the area, it's going to take twice as much force, triple the area, 3 times as much force, and so on. Galileo doesn't say what the force is in pounds. What he does do is he mentions another experiment that does essentially the same thing. You might imagine, instead of trying to hang weights from this in order to create a vacuum, you might imagine taking the same syringe with open, and in fact, let's kind of cut it off so it's just like a tube, and we dip this into a pool of water, and you take this syringe, like this. These lines aren't very straight, but you get the point. So here's the syringe right here, and we have water in this cup, and we draw the syringe up, and in so doing, we suck the water up into this tube. And what Galileo mentions is that you can suck this water up into the tube, but once the water column gets above a certain height, then you're going to have the water column break. In other words, you'll have the water only stay at a certain height. So let me draw another example of this. So let me drag this over to here. So let's suppose you take this, and you're drawing the water upward. And this isn't really to scale, but you're drawing the water upward with this plunger, like this. And you're going to find that once the water gets to a certain height, then the plunger separates from the surface of the water, and the water does not go any higher than that. What is the height to which it can be pumped? Well, Galileo talks about this. So let's look at the text right here. I'm going to highlight some section of text. This section on page 18, Sagredo says, and I'm just going to read part of this, starting right here and kind of going down. So this paragraph, he says, thanks to this discussion, I have learned the cause of a certain effect which I have long wondered at and despaired of understanding. I once saw a cistern, which had been provided with a pump under the mistaken impression that the water might thus be drawn with less effort or in greater quantity than by means of an ordinary bucket. The stock of the pump carried its sucker and valve in the upper part so that the water was lifted by traction and not by a push, as in the case with pumps in which the sucker is placed lower down. This pump worked perfectly, so long as the water in the cistern stood above a certain level. But below this level, the pump failed to work. When I first noticed this phenomenon, I thought the machine was out of order, but the workman whom I called in to repair it told me the defect was not in the pump, but in the water, which had fallen too low to be raised through such a height. And he added that it was not possible either by a pump or by any other machine working on the principle of attraction to lift water a hair's breadth above 18 cubits. Whether the pump be large or small, this is the extreme limit of the lift. Up to this time, I have been so thoughtless that although I knew a rope or rod of wood or of iron, if sufficiently long, would break by its own weight when held by the upper end, it never occurred to me that the same thing would happen only much more easily to a column of water. And really is not that thing which is attracted in the pump a column of water attached to the upper end and stretched more and more until finally a point is reached where it breaks, like a rope, on account of its excessive weight? So what he's mentioning here is that if you draw water up from a well, if the level of the well is so deep that you're trying to draw it up very high, it cannot get above a height of 18 cubits. That's an older system of measurement. Remember, cubic is about 1.5 feet. So this ends up being about, so the maximum height before the water column breaks is right around 10 meters, if we wanted to use more contemporary units. So if you lift it more than 10 meters, or let's round off to about 30 feet, then the water column will break, exposing a vacuum at the top of the column. So what's the point here? So nature's hatred or abhorrence of a vacuum, as Galileo would say, is limited. That is, she permits, so to speak, a vacuum if you apply a force equivalent to the weight of a 30-foot column of water. So you've got to apply enough force to lift up a 30-foot column of water, and once the height is more than that, the water column weighs too much and it breaks under its own weight. And it just so happens that if this tube right here, if this tube has a cross-sectional area of 1 square inch, so let me erase that just a minute, go back. So if this cross-sectional area here is 1 square inch, it just so happens that the water inside of this tube weighs about 14 pounds. And if the tube had half as much cross-sectional area, it would still be lifted to 18 cubits, but it would be half as much weight. And if the tube was twice as big, it would still be lifted only to 18 cubits or 30 feet before it breaks, but it would weigh more. Okay? So before we go on, I think we're going to take a break, and then what we're going to do next is talk about how Galileo uses this measurement in order to try to understand why it is that copper wires stay together.